For over 60 years, humanity has been venturing into the cosmos. We've walked on the moon, sent rovers to Mars, and dispatched probes to the farthest reaches of our solar system. Every single one of these incredible journeys began the same way, with a chemical rocket. These magnificent machines are monuments to human ingenuity. They operate on a simple, powerful principle. For every action, there is an equal and opposite reaction. By expelling hot gas at tremendous speed, they generate the immense thrust needed to overcome Earth's gravity. But for all their success, they carry a fundamental, inescapable limitation: the tyranny of the rocket equation. First derived by Konstantin Tsiolkovsky over a century ago, this elegant piece of mathematics governs the motion of all rockets. To go faster or further, you need more fuel. But that extra fuel has mass, creating a vicious cycle. The vast majority of a rocket's mass at liftoff, often over 90%, is just propellant, leaving a tiny fraction for the actual spacecraft. Our dreams of space exploration are vast and inspiring. We imagine bustling cities on Mars, research outposts on the moons of Jupiter, and mining operations in the asteroid belt. But our current technology makes these dreams incredibly difficult, expensive, and slow to achieve. Imagine a push so gentle you couldn't even feel it on your skin. This is the world of ion propulsion. It's a technology that seems to defy our intuition, trading brute force for incredible endurance and efficiency. At the heart of an ion drive is a simple process involving atoms and electricity. Xenon gas is bombarded with high-energy electrons, knocking electrons off the atoms and turning them into positively charged ions. These ions are then accelerated by powerful electric fields, shooting them out at up to 90,000 miles per hour. Each individual ion provides a minuscule push, but with trillions expelled every second, they generate constant thrust. Ion drives aren't theoretical. They're proven technology. NASA's Dawn mission used ion thrusters to achieve something impossible with chemical rockets, orbiting two separate celestial bodies in the asteroid belt. If ion drives are the patient marathon runners of space, then nuclear engines are the Olympic sprinters with the stamina of a champion. The concept is both simple and awe-inspiring: to harness the atom itself and turn it into raw, propulsive force. A nuclear thermal propulsion engine uses a compact fission reactor to heat liquid hydrogen to over 2,500 degrees Celsius. At these extreme temperatures, the hydrogen expands explosively and is funneled out at incredibly high speeds. This isn't science fiction. It was almost reality over 50 years ago. The NERVA program from 1955 to 1973 built and tested real functioning nuclear rocket engines, proving the concept was viable. Nuclear thermal propulsion could slash Mars transit time from 9 months to just 3 or 4. This dramatic reduction would minimize crew exposure to radiation and zero-gravity effects, making interplanetary settlement vastly more achievable. Of all advanced propulsion concepts, perhaps none is as elegant and poetic as the light sail. It evokes images of majestic clipper ships navigating the oceans of space, a vast, gossamer-thin sheet designed to catch sunlight itself. Light has momentum. When photons strike a surface and bounce off, they impart a tiny push: radiation pressure. In space's vacuum, this gentle but persistent force can be harnessed by building a large enough, light enough, and reflective enough sail. Light sails have moved from science fiction to reality. Japan's Icaros and the Planetary Society's light sail missions have proven that controlled solar sailing works, actively changing spacecraft orbits using only sunlight pressure. For interstellar travel, light sails pushed by powerful lasers may be our only viable option. Projects like Breakthrough Starshot aim to send tiny probes to Alpha Centauri, sailing on beams of light at significant fractions of light speed. When we compare these technologies, we see a fascinating spectrum. Nuclear thermal offers high thrust for rapid human missions. Ion drives provide the perfect balance for robotic exploration. Light sails offer infinite efficiency for the longest journeys. The future won't be defined by a single perfect engine, but by a diverse fleet of specialized spacecraft. Heavy cargo on efficient ion freighters, rapid human transport on nuclear vessels, and pure exploration on propellantless light sails. We stand at a remarkable turning point, as pivotal as when our ancestors first learned to build ocean-going vessels. The age of fire and brute force is ending. The age of electricity, atoms, and light is about to begin. These technologies will unlock a new golden age of exploration. Ion drives will become the workhorses, nuclear engines will carry humans swiftly between worlds, and light sails will be our first ambassadors to the stars. The ships are being designed, the sails are being woven, and the engines are being forged. Our destiny is not to remain confined to our cradle. The cosmic ocean is calling, and humanity is finally preparing to answer. The universe is vast, filled with more wonders than we can imagine, and it is waiting for us. The development of these propulsion systems is the essential next step in our evolution as a species. The moment we learn to move through space with confidence and purpose.